All right. So as I mentioned that the unit is thermodynamics and heat transfer. And before I talk about the unit itself, probably it's good to just give you a brief information about the unit website and how to get the information from there and where to find your where you can find the lecture materials and other stuff there. So let me share with you the screen now. Yeah, as you can see here, this is the main page of the unit, and to the left side you have these pages title. If you scroll down here, of course, you can find the link for the lecture, and also underneath there is the tutorial class and the room for the class. So you will, when you go to City Campus, you go to level 4, and at room 405, the tutorial will be there. So you'll find your teacher there. So as we said, from 11:30 to 1:30. And the learning guide, actually, unfortunately, they didn't send us the final version of the unit guide. So I will maybe, once I receive it this week, I will upload it here just to give you some information about the type of task that we have and what kind of assessment we're gonna run during the session. But yeah, you have general information here. You have the book, the textbook, if you want to refer to the textbook, the name here, and also you can find it in the library, of course, and there is I believe there is an online version you can also use. And these are the major assessment that we will have. We have 3 quizzes, as you can see here, 3 quizzes during the session. And each quiz 5%, weight 5%. So it is an online quiz, of course, because you can run it. We'll see, like I'll check with the your teacher, tutorial teacher, and see what we can do, because last session both lecture and tutorial were online, so we were doing this online, but we'll find out. But I prefer that even if you go to the lab, to the campus, it's good to have your own laptop with you, because it's good to practice. Like we have some practice that you need to use your own laptop. So if you have laptop, then it's good to take it with you to the campus. If you don't have laptop, then you can always ask at the reception. They will provide you with you can borrow a laptop from them, and you can use it and then return it back. So yeah, it's available there. And then we have tutorial participation, which is 5%. And this is like weekly participation. So every week you have tutorial questions, weight 0.5%. So 10 weeks, 10 tutorial sessions or classes, then you will have 5% total. And then we have 2 practicals, as we said, that probably week 6, or yeah, we'll see, like we'll let you know anyway at that time. But each practical weight 15%. So you can see that it's really a big weight. So 2 practicals, 30%. So if you are attending the practical and then submitting the report the week after, then you will get like something from 30%. It's about maybe 20, 25. It's up, like, it depends on how much, like the way that you present your report. But it's big weight. So with the practical and then final exam, 50%. So as you can see, it's not hard to pass this unit, but you need to be like, need to attend the classes so you can at least understand the content. And because you'll see later on, it's so many things, so many equations there, so many principles. So at the first time you think that it's really hard to manage this, but we will provide you with the formula sheet, so you don't have to memorize the equations, because there are so many complicated equations involved in this unit. So you don't need to memorize them. You only need to understand how to use them, how to apply, where to apply them. So that's actually in terms of assessments. Now, as we said, to the left side here, you can see these subtitles. Probably the most important one is the subject tools. And there is other one here. Yeah, probably because I'm using the teacher version. You should see the materials. I don't know if you can see it from your side. Okay. Yeah. Here we go. Yeah, it was hidden here, sorry. So learning materials, as you can see here. So you go to the learning zone and underneath learning materials, and you click on that one, then you will have the lecture notes, solved examples, tables and figures, and other materials. But what I wanted to show you here, lecture notes, you can find the PDF form of the lecture. So these are all lectures here. Probably you'll find the first two now because I have hidden the other ones. But you can download these and keep it on your desktop. And also, you can find the solved examples. I put solved examples for all lectures. It's really good. These examples actually from the book. So I just took grab few examples related to the lecture, and you can always refer to these ones. Try to do some exercise or just solve it or follow the solution here just to understand how they solve these examples. And probably some of them will be like similar to the quiz or example, right? So that's in brief where to find your information. Also, probably the practical reports you can find here, and the tutorial participation. In the tutorial here, if you click on the tutorial, you'll find tutorial questions. So it's all in one document for the whole session. So you can download this document, and it has the tutorial questions for every week. So like for example here, this is for week 1, tutorial 1, and then tutorial 2, and so on. So just in one document, so you can download it and solve it week by week. Okay, and every week, let's say second week, we will give you the solution of this tutorial. So you need to bring it the first week, solve it, and with the teacher in the class, he will give you guidelines how to solve it, and maybe they give you a solution. And then if you provide the teacher with with the written solution, then you'll get 0.5%. So for 10, you get 5%. Okay. Any question? So that's actually in brief about the website. So probably it's good to start now. We already spent 25 minutes, and I think still have same number of students. Actually, we have 3 students only. Okay, so this lecture is just introduction about thermodynamics and heat transfer, and we give you just basic concepts, nothing actually complicated here. Most likely it's a revision for the knowledge or the information you had before, for example, in physics and other units. So application area of thermal sciences. Thermal sciences are commonly encountered in many engineering systems. You can find the thermal science in refrigeration system, air conditioning system, any heating system in industry requires thermal science. Engine and prime movers and thermal power plants. So these are like just major systems, but there are so many other systems. Probably say, for example, renewable energy systems, solar applications, solar thermal or solar PV systems, or wind power. Many things actually, many systems. So, but these are like the major systems you find thermal science there. Okay. The thermal sciences are studied under subcategories, 2 subcategories actually. Thermodynamics, which is the first part of this course. So thermodynamics consists of 2 major laws. I mean, these 2 major laws will drive us to the most thermodynamics systems or principles. So we have first law of thermodynamics. Sometimes they call it conservation of energy. And the second law of thermodynamics, which deals with energy quality. So we have energy quantity covered by first law of thermodynamics, how much energy we have, for example, in the system, in and out, in the balance of the energy. And the second law deals with the quality of the energy. So there's energy, quantity of energy and quality of energy. Okay, and we'll come to this later on. But the second category is heat transfer, and heat transfer also required in thermal science. And heat transfer, which is the form of energy that can be transferred from one system to another as a result of temperature difference. So whenever you have temperature difference, then you know that there is heat transfer in and out. Outside temperature, for example, 10 degree, inside temperature is 20 degree, then there must be heat transfer from inside to outside. Okay, but before we proceed in thermodynamics and then heat transfer, so we will have six weeks. We will study thermodynamics, and then another 6 weeks we will have heat transfer. You will find it, as I mentioned before, you find it is too much information in these 13 weeks or 12 weeks, but you will have an idea about the major topics in both categories. because in some institution they give a course only for thermodynamics and another course for heat transfer. So you can imagine, like, it's because of its so many topics involved in these two. Each one of them is required to be running in an individual course. But in this course, we'll have both of them. So later on, for example, if you have any research or any project you need to expand your knowledge, then you know the major topics in each of these categories, and then you can improve or you can increase your knowledge by referring to the book I have provided or other references. Okay, so to understand the thermodynamics or heat transfer topics, you need to have the principles, some principles, because otherwise, without these principles, it's really very hard to progress well in your study. Dimensions and units, of course, everyone, I believe that you know these things, you know dimensions and units, and you know that in engineering, giving a number without a unit doesn't mean anything. For example, if I say my weight is my weight, for example, 60, and without giving any unit, doesn't mean anything. What's 60? 60 kilograms, 60 Newton, 60 what? So I have to mention the unit after any number. So there are primary units or primary dimensions such as mass, length, time, and temperature T. These are called primary. And from the primary, we can develop secondary units such as energy, volume, and so on. Right? So, and there are two types of units used these days, but most likely it's the first one is the most popular one worldwide. The SI International System of Units. And in SI unit, we give the mass kilogram, the length meter, the time second, and so on. This is like you'll find this unit in most of the books these days. There are a few books, let's say, especially the one from US, they still use the English unit, the pound and foot, and these are like actually very few books these days. So most of them, you'll find it in SI units. So we will, of course, use the SI units. And there's other thing that when you do like any equation in engineering in general, you have to consider the dimensional homogeneity. And what I mean by that, for example, if you have in one side of the equation or within the equation, you have a term in kilojoule per second. In other term, there is joule per second. You should convert one of them to the other, either to make kilojoule joule or convert the joule to kilojoule so that you have homogeneity in dimensions. All right. If you need any question, please, you can stop me anytime. Don't feel shy. So if you don't understand, let me know, please. Okay. And also there are other information or principles we need to know before we progress in thermodynamics or heat transfer. Some definitions such as closed system and open system. What do you mean by closed system and open system? Closed system, also known as a control mass system. And this system consists of a fixed amount of mass. So the mass don't change and don't leave the system or don't enter the system always rotates in the system. Okay, such as this engine. You can see this. This is a cross section of a vehicle engine, and as you can see, there is water, cooling water circulates inside. So you can see here, there's this water circulates inside the engine to cool the engine always, because otherwise, if you are not cooling the engine, then of course the temperature will rise, and then the metal will start to melt. The cast of the engine will melt. So there is always cooling water circulating in the engine, and we call this circulation or this cooling water system a closed system, because there is no extra water coming from outside, for example, or the water doesn't leave the system to other part or outside the system. So it's always within the system, circulated inside the system. So they call this closed system. And sometimes a closed system, a part of the closed system can be considered as open system. I'll show you later on. But for example, let me then give you a definition for open system. So an open system, also known as a control volume, usually encloses a device that involves mass, such as a turbine, a compressor, or a tank, a water tank. So for example, this water tank here, if you look at this, the system here, this is a hot water tank. There is water coming, cold water coming from this side, from the main, and then leaves the tank once it gets heated to the household, for example. So we always have mass in m dot water entering the system or entering the tank, and there is m dot water leaving the tank. So we call the system open system because the mass crossing the boundary of the system. All right. So as I said, we can take part of the closed system and make it as an open system. For example, for this engine, this one, I can take only the boundary. My boundary is this one. All right. If I take this boundary, then I can see that there's water crossing the boundary here, going to the radiator, and there is water coming from the radiator entering the boundary. So in this case, I can say part of the engine, I can make it an open system, all right, and then do my analysis on that part as an open system. Okay, so this is just a definition. Later on, we'll go into details later on. But any question before we move?
No, sir. Thank you.
No, sir.
Okay. So then what else need to mention here? There are also other definitions like properties of a system. So property, any characteristics of a system is called property. Then such as the pressure, temperature, volume, or mass. So we can the property of, let's say, this system in volume as one cubic meter or 2 cubic meter. So you can give a property of the system that this is the size of the system. This is the volume of the system. Okay, so that's what we mean by property. And property could be, let's say, pressure, temperature, as we said, or volume or mass. And property can be like either intensive or extensive. You don't have to be like, to worry too much about this definition, but just give you an idea. What do you mean by intensive property? Intensive property, or intensive properties are those that are independent of mass of the system. So for example, if I have, let's say, a room, and I measure the temperature and pressure of the room, then if I take part of the room, So part of the mass of the room and measure the temperature and pressure, I'll find the same temperature and pressure. So the mass doesn't affect the property. So we call this property intensive property, all right? And extensive property, those properties that, or those values depend on the size of the system. Okay, so let me give you, let's say, an example, the way that we can clarify this. For example, if I have two tanks, okay, the tank number 1, tank number 2. So the first tank number 1, I can call the property of the tank, the volume property is 5 cubic meter. Now, if I split the tank with an imaginary wall, does the volume change? So I have, let's say, two tanks. Definitely the volume will change because I have 2 volumes now. Rather than have 5 cubic meter, I will have 2.5, correct? So you can see here the volume reduced to 2.5 and here 2.5. So we call this extensive property, extensive property, because it changed when I change the mass to part of the mass, the volume, of course, will change. Now, if I go to the second tank property in temperature and pressure, if I split the tank into 2 tanks, I still have the same pressure and temperature, because what I did basically just put a wall between them and nothing happened. Only the mass changed, but the temperature didn't change, or pressure didn't change. Okay. Okay. Right. So they have also other definitions. I believe you know these definitions from physics. So I'll not take too much time, but maybe you can revisit these definitions later on by yourself. So we have, let's say, for example, definition of density. And as you can see, density here consists of two properties, to mass and volume. So it's kilogram per cubic meter. Okay, and we have specific volume, for example, and specific volume actually, it's defined as the volume per unit mass. So, or 1 over density. There is specific gravity, and probably you'll find this property in many questions. And specific gravity actually relates to the ratio between the water density, or sorry, the substance density to water density. So we'll take water as a reference for us, and because we know the water density at atmospheric pressure, it's 1,000 kilogram per cubic meter. So if I divide any material, any substance density over the water density, I'll get what we call specific gravity. Okay, so in some question, they will give you specific gravity. So if you have specific gravity and you know the water density, because it's at standard, let's say, conditions, 1,000, so you can find the unknown density of the material or the substance. Okay. So you can say density of any substance, it's equal to specific gravity multiplied by the water density. Okay. And also there is specific weight. Yeah, so, and also, yeah, this is like another definition. So it's Newton per cubic meter. Okay, there's other definition, which is the state of any state of a system and equilibrium of a system, or state of equilibrium, what we call. So we knew that there is a property now, but one property doesn't give us a state. To find the state, you need most likely two properties of a system to find out what the state of the system or state of any liquid or fluid. So a set of properties that completely describe the condition of a system. Okay, and equilibrium is a state of balance. So, for example, let me take here. Yeah, for example, this example here. For example, this space has different temperatures in different parts. So, for example, if I have a room and one side of the room have 20 Celsius, other side has 42 Celsius, the other one has 23 Celsius, and I say that this space or this, let's say, gas in an equilibrium state. So if I leave it for a while, then there will be heat transfer between different parts. So we said before that the heat transfer will take place from the high temperature to the low temperature. So for example, from this part, we'll go to the other part, try to exchange heat with that part, and then this one, for example, this one, and so on until the heat, until we reach a state of equilibrium. So after a while, if you leave this for a while, then you'll find that all the part of the space, for example, stand at 32 Celsius, means that we reach to the state of equilibrium. So all the temperature everywhere in the system is the same. Okay. Right. And this is like another example with a system at two states. The system here, for example, this one has the same liquid, same amount of liquid, 2 kilograms of liquid or gas. And then, for example, after we provide heat to the tank, the liquid or the fluid the temperature of the liquid start to increase. And then because of the increase of the temperature, the volume will increase. And then it will be like, bigger volume. So now we have two states, state 1 and state 2, for the same amount of fluid. Okay. And also we have another definition, which is the compressible system or compressible fluid. Sometimes they call it compressible and incompressible. But just in brief, the compressible fluid, incompressible fluid, for example, for water, if you try to apply pressure on the water in a cylinder, you find that you can't change the volume of that water because the water is incompressible fluid. And for incompressible fluid, you can define the state with two properties only, like temperature and pressure, or for example, temperature and specific volume and so on, or temperature and density, okay? That's for incompressible. For the compressible fluid, for example, steam, if you put a steam in a cylinder and try to apply pressure on that, you'll find that you can reduce the space or reduce the volume. So this is compressible fluid, and for compressible fluid, two properties is not enough to define the state. You need to have more than two properties. Okay, so we'll come to this later on, but just to give you an idea. Okay. How do you find it so far, guys?
Yeah, good, sir.
Yeah, all good?
Yes, sir.
Makes
Okay.
sense.
Okay. Right. So there is other definition: process and cycle. So a process is if there's a change or any change that a system undergoes from one equilibrium state to another equilibrium state, then we call this a process. Okay, so if I have, let's say, for example, I have temperature and pressure here, temperature 1, pressure for a certain fluid, and suddenly this is at state, at the equilibrium state, and then it happens that we provide, for example, heat, and the fluid temperature of the fluid start to increase to another temperature and pressure, and we call this path, we call it a process, because this is the path that the system undergoes to reach to the second equilibrium state, T2 and P2, right? So, and there are many types of process. We have 3 major types: isothermal process, and this is where we have fixed temperature. So temperature always stays constant, doesn't change. Other properties change, but temperature stays constant. Such as this, for example, this example. So we have state 1 to state 2, but the temperature always constant. So we are increasing, or actually we are decreasing the volume, increasing the pressure. Okay, and so for example, a piston here, so we are increasing the pressure and decreasing the volume, but the temperature always stay constant. So we call this isothermal process. And also there is a constant pressure process, which is we call isobaric process. We have always constant pressure, such as this example. Same thing. We have state 1 and state 2. You can see that always the pressure is constant at 60 bar or 60 psi. And while we're having constant pressure, we still have change in volume. As you can see, from V1 to V2, the volume has changed, and also the temperature will change, because as you can see here, we have heat added to the system. Okay. And the third one is what we call it isochoric or isometric process. And this is a process where we have always constant specific volume. Okay. So as you can see, each one of them can be has a process, its own process, as a constant pressure or constant temperature or constant volume. Okay. So this is these are the types of process we have in thermodynamics. Probably you can refer later on to this video. I don't know if I have time here. Let's show it to you. This will show you an example of the process animation. Yeah. This is not part of the video, of course. So as you can see here, this is isobaric process. The pressure always constant. So while we are heating this, the piston is going up because the volume increased. As you can see to the right side, the temperature also increases. The thermometer here shows the increase in temperature. So we have increase in temperature, and because of the heat added to the system, but we have always constant pressure. And how do we maintain the constant pressure? By putting constant load on the piston. So this is the W, the weight. Always we have the same weight, so we have always the same pressure exerted on the system. So you can see here, this is the PV diagram. you can see that pressure line is always horizontal, which means that constant pressure line. Okay, so that's animation of isobaric process. Okay, the other type is sorry. Maybe this one also show you. Yeah. Yeah, this is another example of isothermal process. So, for example, here, as you can see, we are providing heat, but the temperature scale is always constant, doesn't rise. If you look at the temperature at the thermometer, there is no increase in the temperature, which means that how to maintain this, actually, we provide heat, but always we keep, for example, cooling from this side. We have heat in and heat out. So probably we always keep it temperatures constant if we have try to manage the heat transfer within the system to keep the temperature constant. But as you look to the PV diagram, both pressure and volume changes, right? So both of them are changing. Volume for the first one, pressure different from the second one, different from the last one, and so on. Okay. So this is like isothermal process. Okay. Okay. All right. Back to the lecture. Now, there is a sorry. There is a process which is identical, or it's does not exist in real life, but we call it. We use it because sometimes in engineering design we refer to an ideal process. We refer to the ideal process, first of all, to start our analysis with minimum change or requirement or variables. And then once we know the ideal case, try to add more factors or more variables to make it a real case. So we call this process Gaussian-Equilibrium process. And we will not go into details here, but just let you know what does it mean. So if we have a slow motion piston and cylinder system, so if we can press this cylinder with a slow motion, so it will progress slowly inside the cylinder. This slow motion will reduce or will eliminate any losses can be associated with the movement of the piston inside the cylinder. So there'll be no, let's say, friction losses, for example, or there is no sudden change in fluid properties during the process. And because of this, it will be ideal process. And we call this Gaussian-Equilibrium process. Okay, and as we said, it is used in some engineering design, but there is a question why, as an engineer, we are interested in a Gaussian process for many reasons. Firstly, they are easy to analyze, as we said. And second, work producing devices deliver the most work. It's ideal. So because it's ideal, we can get the most of it. So the output will be more than the actual or real life process. And we can compare any actual process, how much this actual process is good, when we can decide this by comparing the actual process with the ideal process, which is the Gaussian equilibrium process. Okay, so these are actually the reason why we sometimes use the Gaussian equilibrium process. So don't worry too much about this definition, but just to keep it in your mind that when it ever comes in the content of the course, just remember this is like, you know, an ideal case. Okay, there is we mentioned that we have first law of thermodynamics, and also we have second law of thermodynamics, and there is what we call also zero law of thermodynamics. This is like, you know, it's actually a definition. We can't say it's a law, it's a definition, and it's really common sense law. Every one of you now can have can explain this law. If you just, I give you now an example. Before let me check with you now. Before I talk about the law itself, I will give you an example and you tell me what's going to happen. So for example, if I have two systems, if I have two systems, system 1 and system 2, both of them are at equilibrium condition. Okay, if these two objects are attached to the third object, are these also in equilibrium with the third one? Are these two in equilibrium with the third one? Can someone tell me? If these two objects, 1 and 2, are in equilibrium state, in the meantime, they are attached to third object, are they also in equilibrium with the third one?
Yes, I believe so.
Perfect. Yeah, that's the common sense. Look, thank you. So that's what we said actually. If this one, let's say at 25 degree, for example, at 30 degree, and this one also at 30 degree. Okay, so this one, because it's attached to them, should be also at 30 degree. That's common sense, right? Because it's going to be heat transfer between these three objects, and after a certain time, they will come to a equilibrium state. So that's actually the zero law of thermodynamics. As you can see, it's common sense, common sense law. So if two objects are in thermal equilibrium with a third body, then they are also in thermal equilibrium with the other object or other body. So as we said here, two of these are at 50 Celsius. Definitely the third one will be also at 50. Okay. Also, we need to know the temperature scale. Temperature scale. We mentioned before that we use SI units. So in SI units, we're going to use the Celsius. We don't use Fahrenheit. Okay, but just to let you know that there is this kind of temperature scales. If you come to this kind of scale in the future, you know that this is Fahrenheit. We don't use it. We use the Celsius one. But also it's good to know how to convert Fahrenheit to Celsius, because sometimes, for example, you are doing a research and you come to a paper, for example, journal paper published somewhere in other side of the world, maybe US, or they still use Fahrenheit. So you can always know how to convert. I know that there is online conversion unit, you can always use it. But just in case, if you don't have this access, you don't have this facility, then you know how to convert Fahrenheit to Celsius. But in Celsius, sometimes we need to use the Kelvin scale. And the Kelvin scale is the Celsius temperature plus the 273. And you need to use this like in some equations, especially in heat transfer, especially when you have the temperature is to the power more than 1, to power 2, to power 4, then you need to use the Kelvin. Otherwise, you get wrong answer. Okay?
So do you
Right.
get the exact number 273.15 or just?
Yeah, no, you just can use 273. It's enough. Yeah, it will not make big difference. Yeah, but this is like, to have accurate value. This is 273.15. But in our application, we will use the 273. Okay. Okay. This figure will just show you both scale, where do they intersect, like for different gases and different pressure. For example, the Kelvin scale will intersect at 0 Kelvin. And for the Celsius scale, you will find that it will intersect at minus, which is, that's why we add 273. So that's, the scale, the Kelvin scale on PT diagram. Okay. The pressure, we still have something to mention here about the pressure, because we talked about the pressure, the temperature, the volume. We still need to know some definitions, pressure definitions. There are 3 major or four major definitions for pressure. We have absolute pressure. So the absolute pressure measured relative to absolute vacuum. There's gauge pressure relative to the local atmospheric pressure. Gauge pressure can be positive or negative. So if it's negative, then it's vacuum. It's positive, then it's above atmosphere. And there is vacuum pressure, the pressure below atmosphere pressure, and we call vacuum pressure. We call it vacuum pressure. Okay, the unit of pressure, you know it. So we have different units, but the relation between these different units, you can find it here. There is megapascal, kilopascal, and pascal. These are the Pascal scale. And relative to the Pascal scale, we have bar. So we have 1 bar, which is equal to 10 to power 5 Pascal. And we have 1 atmosphere. So 1 bar actually means basically it's almost equal to 1 atmosphere. So 1 atmosphere is in Pascal, it's equal to 101, 325 Pascal. Okay, just make sure that when you solve any question, try to convert the units.
Excuse me, sir.
Correctly, yes.
I think the megapascal and kilopascal are wrong. I think they should be different.
So 1 megapascal
should be 10 to the 6 Pascal, and kilopascal should be 1000.
So he's right as well. He's KPA.
Oh yeah. I got it. Sorry.
It's kilopascal and Pascal. Yeah.
All right, got it.
So that's kilopascal and this is Pascal. All right. But this one is say 1 atmosphere. It's also equals to 1.103 kilopascal. If you want to put it in kilopascal. Okay, or 1 bar is equal to 100 kilopascal. Also, you can do it this way. Okay. All right. So now if you want to show it on, like, just make it clear for you. So when you say this is the, actually, this is the reference line, which is the atmospheric pressure. And then anything above atmosphere, we said it is the gauge pressure. So P gauge, that's coming above the atmosphere, and this is the P atmosphere, so this P gauge. If I add them together, I will get P absolute. So P absolute is actually here, absolute pressure is equal to P gauge, or P atmosphere first, plus P gauge. Okay. In case of vacuum, again, you can see here P atmosphere the same, but in vacuum, we are below the system has pressure below the atmosphere. As you can see here, so it's below the atmosphere, so it's minus. So now we want to find P absolute here. The P absolute also must be the addition of both this one and this one. So if I say P atmosphere, rather than say plus, it will be minus because pressure here in minus. So minus P vacuum. Okay. So that's a difference between both type of different type of pressures. Okay, so we'll have a practice very soon. We can still have time, I think. Yeah. Okay, so any question? Let's do practice, and then you'll understand this. Just before we do the example here, also, we have like a pressure in a fluid, depends on the depth of the fluid. Where are you? Where is the point in the fluid itself? So if I have a tank like this, so the tank at different depth will have different pressure. So at each point of these points, we have different pressure. We call this gauge pressure because this is the system pressure. So we always say gauge pressure for the system. So above the system, there's extra pressure here. This is P atmosphere. So when I want to find P absolute for this case, then I can say P atmosphere exerting on the surface of the tank, surface of the water, for example, plus the P gauge. And the P gauge here, actually, it's the depth of the water multiplied by the density multiplied by the gravity. So as you can see here, P gauge presented by this equation, rho GH. So if I add it to this equation, I'll get the absolute pressure. Okay. And also in pressure, there's a well-known law, which we call it Pascal's law. And the Pascal's law, one of the benefits of Pascal's law, that this law is states that in a system, like in a closed system, the pressure anywhere in the system is the same. Okay, so for example, if you know that, let's say in a hydraulic system of a service center, a car service center, you know that there is a platform that you can raise the car. So there is a platform that where the car comes over, and then a hydraulic system that can lift the car up. So this system, the one like here, because of the Pascal law, we can exert small amount of force to raise the car here, because if we increase the area, here. And because we have balance in pressure, the pressure of both sides is same, as you can see from this equation. P1 is equal to P2, the pressure is the same based on Pascal law. So we can play with the area. So I can say I have force 1 divided by area 1, which is the area of the piston here from this side. It should be equal to force 2 divided by A2. Okay, so the more area here I have, okay, the more area here, the less force I need on the other side. Okay. Okay, clear? So that's one of the application of the Pascal law, relates to the pressure. Okay, so let's go to a couple of questions. For example, the example 1 here, it says that a vacuum gauge connected to a chamber, and this gauge reads 40 kilopascal. So from the name here, vacuum means immediately you know that this is negative or positive? Yeah.
Negative.
Negative. Yeah, thank you. It's negative. So now I know this is vacuum. We go back to our definition for P absolute. We know that now P absolute is P atmosphere minus the vacuum pressure, right? So you determine the absolute pressure. Just simply you apply this and then you find the absolute pressure. Okay. The second example, in this example, we have what we call a barometer. I think you know this from physics. A barometer, it's a device to measure the atmospheric pressure. So in this device, we have a tube filled with mercury. And when you put the tube inside a tank filled with mercury, you'll find that the mercury will have fixed level, doesn't go down, will stop at a certain level. This is because of the exerted pressure on the mercury, the pressure coming from the atmosphere, try to keep the mercury up. And we know that at this site, this is the atmospheric pressure based on the height of the mercury tube or the mercury level in the tube. Okay, so here it said determine the atmospheric pressure at a location where the barometric reading is 740 millimeter. So we know the level here. We know the level, which is 740 millimeter. And you can see the units here, some of them in millimeter, some of them in meter, the gravity, and other one in meter, density in meter also. So we need to make homogeneity in units, as we mentioned before. So either you change one of them, the smallest to the highest, or the highest to the smaller unit. That's, I think, much easier to change this millimeter to meter rather than changing all these units to millimeter. Correct? So what do you think here? How to find the atmospheric pressure from this information? Any idea? Based on what we mentioned before. Because the system now open.
Yes, we can find the gauge pressure.
Yeah. So P gauge, yeah, P gauge here.
Rho GH.
Should be, because we are now in equilibrium state. We said the level of the mercury is fixed at a certain point here, doesn't go down anymore. So it means that the atmospheric pressure is equal to the mercury pressure, correct? So therefore we can say peak gauge is equal to,
Rho GH.
yeah,
So
okay. Right, I understand that peak gauge should equal to P atmosphere because they are at equilibrium, but we don't know P atmosphere, but we can get P gauge, right? So we said P gauge is equal to rho GH, correct? And we mentioned that density in kilogram cubic meter, so we're going to use the same units, we'll not change it here. And gravity,
9.81.
yes. And you can see also the units are meter per second square. And the last one is the height of the mercury, H. So H, if I want to change it to
0.74.
correct, 0.74. Thank you. So you can see here, at the end, we should have Newton per square meter, because remember we said pressure unit is Newton per square meter, right? Or Pascal, or but the first, like the initial one, is Newton per square meter, which we can equivalent to Pascal. So to achieve Newton per square meter, we have to have the same level of units. Now, how do you find, how do we get Newton per square meter? As you can see, Newton, what's a Newton? Anyone remember the unit of the Newton is?
kg meter per square second.
Kilogram meter, correct, per square second, yep. So if I take this part, this is the Newton part, all right? And meter here goes with meter here, we left with square. And we end up with the Newton per square meter, which is, this is the pressure unit. So our solution is correct, or our units are correct. Okay. Any question?
Yeah, I got a question here.
Yeah.
We know that atmospheric pressure is 1,001 point something, right? Or 100
Not necessarily, because it depends on the site.
Oh, so it may fluctuate, right?
Yeah, exactly. So that's why here it tells us that they need the atmospheric pressure, because at this site we have this this H, but probably another site we have different H. So sea level, for example, sea level, it's
760 mm of Hg, right?
yeah, or 101 kilopascal. If you go to the, let's say, mountain site, you'll find this is a bit lower.
Also, atmospheric pressure also does differ from place to place. This is what
Yeah, exactly. Yeah. Yeah, we'll explain this maybe later on. Okay. So that's yeah, solution here. And this is another example, there's a device used in some experiments in engineering. We call it manometer. And the manometer is actually a U-tube, as you can see here. It's a U-tube filled with mercury or any liquid. So for example, here in this, we have a manometer connected to a tank. So what happens actually, the pressure inside the tank try to exert, or the tank or the fluid in the tank try to exert a pressure on the fluid inside the manometer. And as you can see, it pushed, there's a lift that lifted up to 55 centimeter. So this means that the pressure inside the tank is more than the liquid pressure. Otherwise, if it's liquid pressure higher, then this liquid will go inside the tank rather than the other way around. So we know that the pressure inside the tank is greater than the liquid pressure. That's why it pushed the liquid up from this side, not from the other side. Okay, so we know now how much weight exerted by the liquid of 55 centimeter. And we know that the atmospheric pressure is already given. Okay. The gravity, the density of the liquid, we don't know it, but we know the specific gravity. Remember the definition of specific gravity we mentioned before. Specific gravity is density of any fluid or liquid divided by the water density. So we know the density of water, standard density is 1000. I can find what's the density of this liquid inside the tube. So just simply say 1000 multiplied by 0.85, it's 850. This is the density of the liquid inside the tube. I can use it to find the P gauge. Okay, so what we need here to determine the absolute pressure. So we said before, absolute pressure is equal to P gauge plus the atmosphere. So all these are given. Atmosphere is already known. We need to know the gauge. And the gauge is referring to the equation rho GH. We can find the gauge pressure. And then, of course, we can find the absolute pressure. Okay, clear? So, yeah, just simply apply this, and you can find the. I need you to find it later. Like, try to find this yourself, please, and let me know next week if you couldn't find the answer. But it should be straightforward. Just substitute the values, and you'll get the answer. Okay, so by this example, we finish our lecture today. Would you like to ask any question? Because we still actually have a thought that we start 10:30. We still have half an hour.
Yes, sir. In the last example, to calculate the absolute pressure, we did negative, right? Negative PZ plus atmospheric, right?
Yes, yes.
But here, yeah, this was the one.
Yeah. So what we did actually, so we said that this is the reference. Our reference is P atmosphere. So this is a same at a certain site. Okay, and we said that if the pressure above atmosphere, then will be P gauge. If it's below atmosphere, we call it P vacuum.
Okay. Yeah.
Okay, and now to find the absolute always this one plus this or plus this. Okay, depends on the system. So if you have vacuum, then it will be vacuum plus P atmosphere to get P absolute, right? Or other way around. If it's above atmosphere, then it's P gauge plus
P atmosphere.
Yeah, P atmosphere. Okay. So yeah, it's like straightforward. So it's not.
Yeah. So can we go to the next slide, sir, please? The last question.
Yes. Yeah.
Here the atmospheric pressure is top, right?
Yeah. So because you can see here, it's open. The tube is open.
Yeah.
So let's see. Activate my pen. So as you can see here, the tube is open, so it's exposed to the atmosphere. So there is always pressure here, which will gave us the pressure 96 kilopascal, always exerted on the top of the fluid here, trying to push the fluid downward. From the other side, the system pressure trying to push it upward. Correct? So until we reach to an equilibrium state where the level is fixed. When we reach to this state, we know that from one side, the pressure of the system trying to stop the pressure of the atmosphere. Okay. So to find out the absolute pressure, we should add this P, which is P gauge, to the atmosphere, P atmosphere here. So we add this to this one to find the absolute.
To me, it looks like the liquid position is down, so that it should be negative. That's my question was.
This one?
The liquid I mean the tank is downward from the atmosphere, right? If you take the atmospheric pressure as a reference line, and the position of the tank is downwards, right? So
yeah, but this is nothing to do with the actually pressure. If the tank downward or upward, you look to the tube. This tube. So because this is the gauge. We will come to a different type of gauges used in experiments. There is what called boarding gauge like this.
Yeah, there is some more
like a pointer, and you can find. But this is a manometer. Sometimes this is more accurate than this one, because this is relates to the density of the fluid. So if we have a pure substance inside the tube, you know the density of the substance, you can have exact measure of the pressure. So now your question says the tank is below. Yeah. Actually, you don't look to the tank, you just look to the tube itself and see the level of the fluid or the liquid inside. So let me let's say give you another example. If I have the same tank here, okay, and I have YouTube, same thing. And same thing, the tube is open to the atmosphere. So I'd ask you a question about this now. So if I have the level of the liquid in the tube is this. So one side close to the tank is high, the other side close to the atmosphere is lower. So what do you think here? Are we the pressure of the tank is below atmosphere or above atmosphere? What do you think? Okay, you can see here, this side, this one here is higher from other side, the side of atmosphere. While here it's higher from the side of the tank.
Yeah,
so
the tank pressure is lower than atmosphere.
Yeah, so it's under vacuum here.
Yeah, because it's going downward. The reference point you were taking the bottom, right?
Yes. So normally the YouTube, for example, this is YouTube. If you are in equilibrium state, nothing happened, like there's no pressure. The liquid is, for example, like this, both sides of the liquid at the same level. But when you exert a pressure from here or pressure from this side, okay, either it will raise up here like this or rise from this side. Depends on which one is higher, which side is higher pressure, right?
Okay, yeah.
So for this case, sorry. Yeah, so for this case, we have this one. You can see that it's pushing the liquid upward from the atmosphere side. So sorry, pushing the liquid downward from atmosphere side and upward from the tank side. Okay, and let's say if it's happened that the atmosphere is much higher than the tank, so the vacuum in the tank is too big, you will find that this liquid will flow inside because the tank pressure cannot stop the fluid from coming inside the tank. Correct?
Okay, but if it is like vacuum pressure, then of course negative will take, but and other way we have to differentiate it, right? In terms of height, like which
So
reference.
sorry, I didn't get your question. Can you say it again, please?
Like in the first question, there was saying that the question itself says it's vacuum pressure, so we took negative, right, in the first place.
This question, you mean?
No, yeah, the first question or second last, the last slide.
No, this one. This one.
Yeah, it's clear. It's mine. It's a gauge pressure.
Yeah,
Vacuum.
yeah.
Okay.
Yeah, but this one, yeah, say like this gives you clearly that it's a vacuum. So you know that's vacuum minus. Yeah, but with the manometer, this one you have few questions. You'll find it in the tutorial relate to this one. So this is different. You need to know which side you have H higher. It's if this H high from the atmospheric side, you know that it's above atmosphere. If it's you find it higher from this side, from the tank side, then you know that it's vacuum side.
Low atmosphere. Okay.
Yeah. So just straight forward.
Just terms of height. Okay.
Yeah.
Fine.
Yeah.
Thank you for that.
No worries. Okay, then. So if there is no question, then other question, if you like to ask, happy to answer. Yeah, just make sure that, as we said, so now you will work on tutorial 1.
Whereabouts are those questions, sir?
Yeah, I'll show you again because let me stop sharing, go to the other. Yeah, so if you go to your, the unit site, and we mentioned that, say, first page here, and you can look to the material, learning material, and then underneath there is quizzes, tutorial.
Oh, it's in there, is it?
Assessment zone, there is tutorial participation. So you click on tutorial, you'll find the tutorial questions here. Okay. So you click on tutorial question, and this is the document for all questions during this session. So you start now, if you open this, just do the first one, the first page. Okay. So you can see here, there is an example about the manometer. Look at how it looks like. You have 3 types of fluids. Okay, and you can tell that there's one of them water, there's oil, and there's mercury. So each one of them has different height. You know that the height of the water is pushing this up, and then pushing the oil down here, and then pushing the mercury up. So you know that the pressure inside the tank is higher than the atmosphere. So that's one question. So probably start to work on these questions. Even if you don't know how to do it, you can like try your best And then when you come to the tutorial class next week, you will the teacher will help you. Right.
Excuse me, sir.
Yes.
Will we submit these questions online, or are we going to hand it out to the teacher on the
Because now it's face to face. Well, I think it's better to do it online. It's easier for you, right?
Yes, sir. Submitting
Because,
online is much
so
easier.
I will talk to your teacher and see like how we can
All
manage
right.
this. But it's
Yeah.
easier, I think, for all of us to submit it online. Better than do it written, because you can always write it on paper and then scan it and upload it online. This is easier for everyone. You could do it from your home.
But they're all due by the next tutorial class, yeah?
Yeah, correct. Yeah.
Yeah.
What else I wanted to say here about the unit? I think I mentioned this. Right. Yeah, I think that's all here. Oh yeah, here we go. This is the schedule. So as you can see, quiz will be week 4, quiz 1. It will cover the 3 weeks topics, and then quiz 2 will be week 8. It will cover from week 5, or sorry, from week 4 to week 7. And so then the last one, quiz 3, covers this from weeks 8 to week 11. And then the final exam at the end. All right. Yeah, and let me check here if there's yeah. Okay, but anyway, you will, if you try to solve this, do your best to solve these questions, the first group of questions. And if you need help, let me know, send me an email, or wait till next week and talk to your teacher. All right. Any other questions, guys?
No, sir, it's all good.
Okay, hopefully this is the first lecture you feel like it's going to be a good exercise for you, and hopefully successful as well. All right.
Thank you, sir.
Okay, thank you for your attendance. We'll see you next week.
See you.
Sir.
Bye.
Bye, sir. Thank you.
Okay.